Valuing the volume under the surface over the circular regions in the rectangular coordinates are a little bit difficult because of this region R is defined as a difficult functions. So let us assume that this R is a circle in the region was the center at 0 and 0 and was the radius R. And in this case, we would define this R as a set of numbers x and y, where the x would change between the minus R and the R, minus radius and plus the radius, and the y would change between the two functions, minus square root of r squared minus x squared and plus square root of r squared minus x squared. Or we need to evaluate a double integration. We need to integrate this function with respect to the y and with respect to the x. But when we need to integrate our function with respect to the y, we need to use the bolus. We need to use these functions as a bolus, which makes our integration very difficult. So fortunately for us, we can use the polar coordinates. We can transform our areas to the polar coordinates and try to evaluate this integral more easier. But before we learn how to do this, so let's discuss how to find the areas on the polar coordinates between the t curves, between the R1 and R2, and the theta is going to change between theta 1 angle until theta 2 angle. So if we would discuss this angle, so we will denote this angle as the delta theta. So in order to find the area here, I would find the area of the sector, of a circular sector, until R2, which would be a 1 over 2 R2 in a square multiplied as a delta theta, and then I would find the area until R1. It would be 1 over 2 R1 in a square multiplied as a delta theta. Then I would just subtract them, and this would give me exactly this area. So I would just take out the 1 over 2 delta theta out of the brackets, and what I would have is R2 in a square minus R1 in a square, and we can rewrite this in the form of 1 over 2 R1 plus R2 multiplied to the RT minus R1 multiplied to the delta theta. And actually RT minus R1 is the difference between these two curves, the distance between these two lines, and it would be the delta R, which is RT minus R1. And our formula becomes 1 over 2 R1 plus RT multiplied to the delta R and delta theta. And actually R1 plus RT is the distance from the origin until the middle of this area. And I would denote this as the R. So this would be R multiplied to the delta R and delta theta. This I would denote as the area, delta A. The area of this region would be R, the radius from the origin until the middle of this region, multiplied to the delta R and delta theta. Now let's discuss how to find the volumes. So in order to do this, we need to split this area into the many small pieces. We would mesh this region by choosing a lot of radiuses, where the distance between the two lines here would be delta R, and the distance and the angle between these two angles would be the delta theta. And if I would choose some of the regions here, this region would be the R, the area of this region. If I would choose this region here, the area of this region would be R, the radius from the origin until here, multiplied to the delta R, multiplied to the delta theta. Analogously, we obtain how we obtained the formula before. So, and then our double integration of a surface with respect to the x and y over the region D would be written as the double integration over the region D f of x y dA. And I can write down this as the double integration of the f of r and theta, when I can write down the x and y in the polar coordinates, multiplied to the dA, which can be written as r dr d theta, or the same region. So we would just transform our curve to the polar coordinates, and we would use this formula in order to evaluate the double integration. So let's do an example. Let's say we would like to integrate this surface over some region D, where this D is the upper plane bounded the T circles. Between the circle and the origin was the radius 1, and was the circle, the origin was the radius T. So graphically, this region D looks like this. So from 1 to the T. So this is our origin between the T circles. So we can define this D in the polar coordinates as the set of points with the distance from the origin R and the theta S. So the R would change, right? So for example, no matter which point I'm choosing inside, the distance from the origin is always between 1 and 2. So this is between 1 and 2. And the theta would change from the 0, right? This is the 0 angle, until theta is equal to the pi, until pi. Then we just need to use the double integration formula for in the polar coordinates 3x plus 4y squared. The double integration of the 3x plus 4y squared dA in the polar coordinates over the region D would be the double integration in the polar coordinates of this function multiplied to the r dr d theta. So this would be the double integration of some function multiplied to the dr d theta and multiplied additionally to the r. So if I would integrate first with respect to the r, it would change from 1 to the 2. Then if I need to integrate this with respect to the theta, it would change from 0 to the pi. So let us rewrite this function in the polar coordinates. In order to do this, we need to substitute the x with the r cosine of theta, and the y we need to substitute with the r sine of theta. This is the formulas of the transformation of the coordinate system. So I would write here 3r squared cosine of theta. Well, let me write this as a 3r cosine of theta plus 4r squared sine square of theta multiplied to the r, and we need to integrate this with respect to the r first. So let's discuss this integration separately. So this integration would be 3r squared cosine of theta plus 4r cubed sine square of theta. Integration with respect to the r from 1 to the 2. This integration would be r cubed of cosine of theta plus r4 sine square of theta, and we need to substitute 1 and 2. If I substitute the 2, it would be 2 in the cube, which is 8, minus 1 in the cube, which is 1. If I subtract them, it would be 7 cosine of theta. And if I substitute the 2 to here, it would be 2 in the power of 4, which is 16, and 1 in the power of 4, which is 1. If I subtract them, it would be plus 15 sine square of theta. Now we need to integrate this function, 7 cosine of theta plus 15 sine square of theta with respect to the theta, where theta changes from 0 to the pi. The first part would be easy, right? The integration of 7 cosine of theta with respect to the theta, it would be 7 sine of theta with the sine of theta between 0 and pi. If I substitute the pi and 0 to the sine, it would be 0 in both of the cases. Interestingly, I can integrate the second part using the formula for the double angle. So I can write down this integration by 15 multiplied to 1 minus cosine of d theta over 2 d theta. So the theta changes from 0 to the pi. So this would be 15 over 2 multiplied to the 1, and its integration is 15 over 2 theta. And integration of the second part would be minus 15 over 4 sine of 2 theta. So if I substitute the 0 and theta, we would get the answer. So in both of the cases, when I substitute the theta to here, I need to substitute this from 0 to the pi. When we substitute the pi to here, it would be sine of 2 pi, which is 0, and sine of 0 is also 0. And 15 over 2 theta would be 15 over 2 pi, 15 over 2 pi. This is our answer. It is indeed much easier to use the polar coordinates here. Now, let's discuss this problem. we need to use the double integration to find the area enclosed by one loop of this rose, which is given with this equation. So let's define first of all the region. This region D is defined as the points was the coordinates r and theta, where the r would change between 0 and the cosine of 2 theta, and the theta would change between this angle, which is theta is equal to the minus pi over 4, and this angle, which is theta is equal to the pi over 4. So the theta would change between minus pi over 4 and pi over 4. We need to find the area, and we would just double integrate some surface. For example, 1, it would just give me the flat area, flat surface, and the height of 1. And we need to integrate this with respect to the x and y. So this would be the same as integrating this one in the polar coordinates, where the r would change from 0 until cosine of 2 theta, multiplied to the r dr d theta, and the theta would change from minus pi over 4 until pi over 4. So let's integrate this first of all with respect to the r. So the integration of the r would be r squared over t, and we need to substitute the 0 in cosine of 2 theta. So this would be cosine square of 2 theta over t. Now we need to integrate this with respect to the theta. So if I would integrate this 1 over t, integration of the cosine square of 2 theta with respect to the theta from minus pi over 4 until pi over 4. I could write this using the formula of the double angle as 1 over 4, the integration from minus pi over 4 until pi over 4, of the 1 plus cosine of 4 theta d theta. And its antiderivative would be 1 over 4 theta plus 1 over 4 sine 4 theta. And we need to substitute minus pi over 4 and pi over 4. So please note that when I substitute the theta with the pi over 4, 4 multiplied to the theta would be pi. And when I substitute the theta with the minus pi over 4, 4 multiplied to the theta would be minus pi. In both of the cases, sine function is equal to the 0. So this would be 1 over 4. So when I substitute this, it would be pi over 4 minus, then I need to substitute this, minus pi over 4, which is pi over 2 here. And if I divide this to the 4, it would be pi over 8. This is the area of this region, and we use the double integral in order to find this area. So we could find this area by using the double integration of the 1 with respect to the x and with respect to the y over this region D, or it would be the same as integration of the 1 multiplied to the r dr d theta, where this region is defined in the polar coordinates.